moving on. So what we're going to do now is use this short circuit, open circuit test method to develop a model for that single phase transformer over there, and then use that model to analyze the circuit with a load connected of 546 ohms and prove that the model reliably predicts the transformer performance at 546 ohms load. Okay, so it kind of proven that all this modeling stuff we've done actually does work. Right? So we're going to work for primary voltage of 400 volts and compare the model prediction with the practical measurements. Alright, so the first thing that we need to do, my table on the board don't look very clear. Right, we're going to do the open circuit test and use a wattmeter. Will tell us what the power is with the open circuit. Wattmeter will tell us what the primary volts is, and the wattmeter in the primary will tell us what the current is, and then the other wattmeter will just be giving us the voltage. It won't have any watts or any current on it because there's no current flow on its open circuit. So that's one test we'll do, and you can record the results in the table. And then on the next page is where we're going to do the short circuit test, and we'll have the wattmeter again just in the primary this side, and we'll measure primary volts, primary current and power in watts. And when I've done this before, I used 40 volts there, so we'll use that again because I know that's safe enough not to draw too much current in the secondary because it's short circuited. Okay, so we'll do those tests now, take those results, and then use those results to develop a model for that transformer. We're going to go through and develop this model for the loaded situation. So you're going to find the value of the two components, the two parallel components, and find what A is. You're going to find the total predicted primary current, the secondary current under load, the voltage at the secondary terminals under load, the active power dissipated by the load resistor, and compare those results to those that we measure. So I'll then connect the whole thing up, primary and secondary, with a load of 546 ohms, and we'll see whether those results compare with what you calculate. Right? So it sounds like quite a lot, but ain't actually that bad. Okay. So if we go over to the rig now, see if we can get some right, primary side wattmeter, secondary side wattmeter. Yeah. So I'm going to apply 400 volts. These two wires here are the load. They're currently disconnected, so it's open circuit. I'm going to apply a primary voltage, 400 volts. That'll do me. 3 significant figures, that's 400 volts. Yep. So we've got a primary voltage of 400 volts. That's telling us the primary power is 3.6 watts. the primary current 20 milliamps, and we get a secondary voltage of 251 volts. That's dodging around a little bit, but that's 251, three significant figures. Yeah. All right. So from that, you'd be able to calculate the values of the parallel resistor and inductor, and you'll also be able to find out what I is from the two voltages. Yeah. Just turn that back down again. Switch off. I'm gonna take that out. Short circuit the secondary. Yeah. Okay. Now I'm going to apply 40 volts to the primary side. So it's a reduced voltage that I've calculated that won't burn the transformer out. Volts. We've now got a primary current of 248 milliamps and a power of 7.2 watts. Alright, so that's our data to develop a model. Batteries. I think there's bloody 6 AA batteries in them. They aren't cheap to be batteries. Let's just record those results on the board as well. So primary on open circuit test, primary power was 3.6 watts. Primary voltage we set to 400. I'm just going to put a note beside that was chosen. Yeah. Primary current 20 milliamps and 251 volts. And then the results for the short circuit test, again, that was a chosen value, 40 volts. Current was 248 milliamps, and power was 7.2 watts. Okay. So if we go back to our open circuit test results, remembering back to the practice question we did, what did we use the power to find? We got PM was equal to 3.6 watts. I've got to be a bit careful here now because the results are slightly different to when I done it last time. It's never going to be exactly the same. What from those results there, what else can we calculate? Apparent power, we can get SM from EP times IP. Yeah? 400 times 0.02. VA. That's rounded correctly, is it? Like, was it exact, is it? Okay. So now we've found that, what can we find? QM, reactive power. How? Yep. Square root of 8 squared minus 3.6 squared. Three point 71 bar. That's a little bit away from what I had last. That's closer to what I had before. 3.71 bar. Alright. I wondered why it was so far away from what we got last. In fact, last time it was 7.14, is it? From those two values, what can we now find? Remembering we're looking at the open circuit model. We can find the value of RC and XM, can't we? From, remember what we done? EP squared over the power, and this one EP squared over the reactive power. Kiloohms. We won't be far out. So we calculated the value of RC from EP squared over the power, 44K, and XM by EP using EP squared over Q, 22 kiloohms. The last thing that we can get from the open circuit test, and the most important thing for the on-load analysis, is I is equal to EP over ES, that's the 400, divided by the secondary voltage, 251, .6. Yeah, 1.6 will do. That's what I had last time we done it. Okay, so that's the open circuit analysis that would leave us with this kind of model. .400 volts. resistor there of 44k, an inductor of 22k, and there's our open circuit transformer, 251 volts. So there's our open circuit situation. Yep. I equals 1.6. All happy? Yep. Now we move on to the use of the short circuit test to find the values of R and X for the on-load analysis. Yep. So what's the first thing that we can calculate? No, I mean, we can get apparent power, but that ain't anything real, is it? Because we're not at the nominal voltage of 400 volts. Looking back at the short circuit test in the example question, what did we find? We found the impedance, didn't we? ZP is equal to the short circuit voltage applied. Remember, these are chosen values, and that's much less than it would be if you were using the transformer, because we've got the secondary short circuited. We end up burning it out if we apply too much primary voltage. Dividing that by impedance as voltage divided by the short circuit current in the primary. 40 volts divided by 0.248 amps. $161 ohms. That'll do. 3 significant figures will do us. Bearing in mind, in our data, the most we got is 3 significant figures, so we can't really include any answer more than that. Yep. Then remember what we're aiming for. Is now we're aiming for the sides of this triangle, R, Z, and X, aren't we? Can we calculate any other? Another one, so we got that one. Can we calculate either R or X from the data we got? This is the one where we had to be careful which one we used, remember? Yeah, we can get R from P short circuit over I short circuit squared. 7.2 over 0.248 squared. Answer 117 ohms. So we now got two sides of the triangle. We can find the third one. XP is equal to the square root of Z squared minus R squared. Square root of Z was 161 squared minus 117 squared. And we get 111 ohms. So now we've got all three sides of our impedance triangle, but more importantly, we found the value of these two components, R and X, for the model. Yeah. So we can write them on here now. R was, please, 117 ohms. X was 111 ohms. Okay. And we're looking at, in the real transformer, applying a load of 546 ohms. So what's the first thing we need to do here? We're looking to calculate, first of all, the current flowing there in the primary, IP. Total predicted primary current. Find IP. Yeah. We need to find the total impedance. What do we need to find first before we can find that? We need to find Z dash. ZL dash is equal to A squared times ZL. And what A was 1.6, wasn't it? Times 546 equals 1398, Richard, yeah? Okay. So we can write that on our model. Z2 dash, or the A squared times Z, is 1398 ohms. So, in a few minutes, finish that off, part A off, to find now the total impedance, and then find the primary current flowing. So first we found IP by first finding the load impedance transferred to the primary side, calculated ZT, got it in polar form, 1519 ohms, used that to find the primary current flowing. And that's something we can measure up there and prove that's the same, or close to it anyway. And then finding I2 was a matter of saying that I2 transferred to the secondary is equal to the primary current flowing. That's what we just calculated. We also know that if we transfer I2 to the secondary side, we do it by dividing by A. So if we multiply I2 dash by A, we end up with I2, 0.421 amps. Does that ring true for a step down transformer? Current is going to go up. So that looks about right. Yeah. Next part of the question was voltage at the secondary terminals under load. What was the easy way to do this? Yeah, we know we know I2 because we just calculated it. We know what Z is. So the easy way to get that is to say that E2 is equal to I2 times Z. 0.421 amps angle minus 4.19 degrees, all times the 546 ohms, was it? And what do we get there? 230 volts angle minus 4.19 degrees. And there's the active power dissipated by the load resistor. We know, so D power in load. First of all, resistive load P equals S, and ignore angles. Yeah, we know that. Therefore, PL is equal to I2 times E2. I2 was, we only want the magnitudes, 0.421 times 230 equals. Sorry? 96.8 watts. Okay. So we've got a range of results there now. Calculated values with primary current. What did we now calculate? 0.263 amps. Secondary current, 0.421 amps. Secondary voltage, 230 volts. And the power at the output, 96.8 watts. Right.